What is particle physics all about? We will look at structureless particles and show how scattering works like a microscope for the tiniest scales. Among the fundamental building blocks is the electron E. The electron is a lepton. There are 3 charged leptons, electron, muon, tau, and in addition 3 neutrinos. For the 6 quarks up and down are central. They build protons and neutrons, which make atomic nuclei. The heaviest known elementary particle is the top quark T, with a mass of about 180 proton masses. Quarks and leptons are matter particles. They have spin 1/2, so they are fermions. Each has an antiparticle. For example, the positron is the antiparticle of the electron. Matter particles interact via exchange particles. We know the mediators for 3 of the 4 fundamental interactions. Electromagnetic via the photon, it binds nuclei and electrons into atoms. Strong via 8 gluons, they hold protons and neutrons together by binding their quarks. And weak via the neutral Z boson and the 2 charged W bosons, W plus and W minus. They drive certain radioactive decays. All these mediators have spin 1. They are vector bosons. For gravity, we do not have a confirmed exchange particle. Of course, all matter particles feel gravity because they have mass, but in particle scattering experiments, gravity plays a negligible role. Now to the Higgs. Through the Higgs mechanism, matter and interaction particles acquire their mass via contact with the Higgs field. The discovery of the Higgs particle in 2012 confirmed this mechanism. The Higgs boson is the only spin-0 elementary particle. Quarks are not found free in nature. They are always bound in hadrons, that is, in combinations with other quarks or antiquarks. Baryons have a 3-quark structure. The best-known baryon is the proton with 2 up quarks and 1 down quark. The neutron has 1 up quark and 2 down quarks. Mesons are quark-antiquark states. For example, the positively charged pion, pi+, consists of an up quark and an anti-down quark. The positively charged kaon, K+, consists of an up quark and an anti-strange quark. Our most important tool for studying particles and their interactions is scattering. Think of scattering as a microscope for the tiniest structures. Here is the idea of the total cross-section. A beam comes in from the left and hits a target foil with 5 scattering centers, such as atomic nuclei in a gold foil. If a beam particle passes through the interaction region around a center, it gets deflected by the angle theta. From above, you see the 5 scattering centers in the target foil. Their effective area is called the cross-section sigma and corresponds to pi times r squared. The area illuminated by the beam is labeled F. With a simple proportion, we can determine sigma from scattering. One view. The probability to scatter equals the area fraction of m target particles, each with area sigma, compared to the illuminated area F. Another view, count rates, the number of scattered particles per unit time .n compared to the number of incoming particles per unit time .ns. Setting these equal lets us extract the cross-section sigma, and thus the microscopic size of the target particles. The number m of scattering centers we convert to centers per volume, thus the target number density n. Since the incoming rate .ns, the target number density n, and the target thickness delta x vary from experiment to experiment, we bundle them into the luminosity L. The total cross-section sigma is the scattered rate .n divided by the luminosity L. We introduce the cross-section as a geometric effective area. In quantum mechanics, scattering is a probability, but we still express it in units of area. Now, let us link the 3 interactions to the total cross-section. In all cases, 2 particles come in, they exchange a mediator particle, and 2 particles go out. For the strong interaction, 2 up quarks from 2 different protons can interact by exchanging a gluon. 2 incoming electrons can scatter electromagnetically by exchanging a photon. Alternatively, they can also scatter via the neutral-weak interaction by exchanging a Z boson. Finally, consider scattering between an electron and an electron neutrino. They exchange a W boson of the charged weak interaction, turning the electron into an electron neutrino and the incoming electron neutrino into an electron. Measurements of total cross-sections across the three interactions show that the strong interaction gives the largest values. Proton-proton scattering is about 100 millibarns. 1 barn, written B, equals 10 to the minus 28 square meters. Electromagnetic scattering, for example, photon-proton, is roughly 1,000 times smaller. Weak processes, such as neutrino-proton, are many orders of magnitude smaller, around 10 femtobarns. These very different cross-section sizes reflect the different strengths of the three interactions. Just like the fine structure constant alpha for electromagnetism, there is alpha S for the strong interaction and alpha W for the weak interaction. In theory, these couplings set the absolute scale of cross-sections. That is it. We met the matter particles, quarks and leptons, and the mediators of the strong electromagnetic and weak interactions, as well as the Higgs boson. We saw how scattering works as a microscope for tiny structures and how a cross-section is defined. Have fun exploring these concepts in more depth.